So today we will start with tertiary structure. Peptide bond. You must mention peptide bond in primary structure. Correct? Without peptide bond, primary structure definition is incomplete. Clear? Fine. Now tertiary structure. Tertiary structure means it is the spatial arrangement of secondary structural elements. That means suppose there is a protein which has 5 alpha helices. 5 alpha helices. They are not going to stay like this. They may stay like this, this. Whatever may be the arrangement. Correct? So these all arrangements are described in 3 dimensions. It is not possible to describe in 2 dimensions. So these arrangements are called tertiary structure. That means how one secondary element is situated with respect to the other secondary elements is called tertiary structure. Now, if there are proteins which has more than one subunit, then the same arrangement may occur between the subunits like secondary elements. So, with respect to one subunit, how the other subunit is located or oriented, that structure is called quaternary structure. So, all proteins will have 3 levels of structure, few will have 4 levels of structure. Who has more than one subunits? Clear? So, tertiary structure we will describe through the structure of myoglobin. Myoglobin stores oxygen and releases oxygen on change of slight PO2. Change of slight PO2. It is a monomer, contains one polypeptide. It stores oxygen in muscle and which has high affinity for O2. If it has high affinity for O2, that means what will happen? It will cling to O2 readily. Correct? Then diving animals. General knowledge. Diving animals. Or are we diving animals? Then how can we increase myoglobin? Anyone who loves football? If you can recall, before Olympic, Asian Games, Indian football team is sent to the higher altitude area for physical training for 1 month or so. Why? Because at high altitude, hemoglobin will increase, muscle will increase myoglobin, so that muscle can store more oxygen, and then when they come down and play the football, they get more energy. Correct? So in both cases, diving animals are the same, where you need to store more oxygen for muscle to exercise. Underwater, they have more higher concentration of myoglobin in the muscle compared to the other animals. Hemoglobin, on the other hand, is found in red blood cells, RBC. Correct? And that's why blood cells are red. It carries oxygen. It stores oxygen. It carries oxygen. Correct? So, it has lower affinity. It has lower affinity. Why? If it has higher affinity, then what will happen? It will never leave the oxygen after reaching the tissue. Correct? That is not desired. So we want to deliver oxygen, not to keep it back. It is a tetramer made up of usually alpha 2 and beta 2. Usually. Why usually? It is HbA1. HbA1 composition is alpha 2 and beta 2. The structure of myoglobin, for which he received the Nobel Prize. This group, Arwin Gis and his co-workers. Now, this particular structure shows it's a globular protein. and it has 8 alpha helices, A, B, C, D, E, F, G, H. They are named as alphabetical order A to H, 8 alpha helices. How many amino acids are there? 153 amino acids are there. Out of them, 70% amino acids are present in these 8 alpha helices. Between E and F helix, there lies a porphyrin ring called heme, which holds the iron atom. Correct? That's all. These are all informations you need to remember regarding structure of myoglobin. Number of amino acids, number of alpha helices, nature of shape, globular protein, and location of heme group. And one more thing will be added, that is distal and proximal histidine. Now listen, I am not going to teach you like kindergarten. You are here, that means you know something about myoglobin. If you don't know, that is your setback. Right? So these are all important points we must remember. The size, what is the size? 45, 35, 25 angstrom. Length, width, and height. Clear? Write down. What else? Being globular protein by nature and being found on Earth. Why Earth? Why I am emphasizing Earth, planet Earth? Because planet Earth is mostly aqueous outside. We have water. Had it been some other planet where water is not available, the structure would have been different. What is the structure? The basic structural feature of any globular protein found on aqueous medium or planet like Earth is that all hydrophobic residues, amino acid residues, are packed inside the structure, away from water outside. So suppose you go to a planet outside solar system and find out one protein, and you find out it has a structural feature like myoglobin. That means that planet has water. The planet has water. Number one. Number two, the material for synthesis of biomolecule in the planet is same as we have in Earth. That is carbon. We are all carbon based. Now, long back when world used to listen radio, All India Radio, Vivid Bharati, all this time. That time one play came in the radio. I remember still. I was very young. So that time one sci-fi, science fiction play came in the radio where some aliens entered into Earth who were invisible. How is it possible they are invisible? Can any one of us be invisible? Yes, it's possible. If we can replace all our carbon molecules with silicon. Carbon and silicon fall under same group in Mendeleev's table. So they have same property. If we replace carbon with silicon, then with a particular angle of sunlight, we all will be invisible. So that was the core essence of the story, how the aliens were invisible. See, long back, before reading Mendeleev table, I learned this from the radio. Beautiful story, isn't it? So these are the basic things of biomolecules which will actually help us to find out life even outside solar system. Now, out of 153 residues, 121 residues are found in these A2H alpha helices. Only polar amino acids inside are 2 histidine molecules. Means what? I said all hydrophobic residues are jutted inside, hydrophilic are jutted outside and hydrophilic are packed inside the structure, except 2. What are those? These 2 histidine molecules, E7 and F8. They are called distal histidine and proximal histidine. Distal means at a distance, proximal means nearer. Correct? So these 2 histidine, although they are hydrophilic, charged, but still they are poked inside, packed well inside the structure. There must be some reason. These are used to hold the heme molecule at place. We will see the structure. F8 is called proximal and E7 is called distal histidine. Now, hemoglobin. Today's class is most important. You will have at least 3 long questions from this class. Structural features of hemoglobin. Can you remember this? Is it difficult? Why not? It's not difficult. Tell me the rule. What was the figures for myoglobin? 45, 35. Correct? All 10-10 difference. Here, all 10-10 difference, but 20 high. 45 became 65, 35 became 55, and 25 became 45. Like this you remember. Correct? Then what else? They are made up of alpha and beta 7 alpha 7 contain 141, beta 7 contain 146 amino acids, which is not same as that in the myoglobin. So out of 153 now it is here 141 and 146 respectively. So what happens? So there is no D helix. That means A, B, C, D, E, F, G, H. D is missing. A, B, C, E, F, G, H. Correct? That means structurally they are all same except D helix is missing. Clear? Now this thing you have to study. This graph, all of you, start this graph. Okay, before you do this graph, first you know these different types of hemoglobin. Hemoglobin at different stage, it is very, very important, I tell you. Throughout the life it will recur. Hemoglobin at different stage of life. Embryonic, fetal and in adult. See, start with adult. How many are there? HbA1, A2 and HbF. Fetal hemoglobin normally presents very low concentration among the adult. If not, the person is suffering from sudden illness, the fetal hemoglobin will not increase. Maximum is HbA1, then comes HbA2. See the difference, alpha 1, beta 2 and A2 is alpha 2, delta 2. HbF is alpha 2, gamma 2. Why we cannot use gamma fetal hemoglobin in adulthood? Because it cannot hold oxygen for prolonged period. It has sharper oxidation curve compared to HbA1. So that will not serve the purpose to deliver oxygen to the distal part of the body. That's why fetal hemoglobin is not a choice of hemoglobin in adults. But it is a choice of hemoglobin in the fetal state. Why? Because in fetal state, oxygen is not carried from lungs. Oxygen is not carried from lungs. Lungs are non-functional. Right? So from the placental source, it will take the oxygen and deliver to the tissue or a fetus. So the route is different. Next, in the fetal state, most of the hemoglobin is this, alpha 2, gamma 2. And in embryonic state, now I'm not going to ask you what is the difference between embryonic state and fetal state, because you haven't studied yet. But we will study. Right? These are all got definite demarcation. Up to this age, it is embryonic state. Beyond this age, it is fetal stage. জল খাও এই ছেলে জল খাও অত বড় বড় হাই তুলিস না সকালবেলা What are these? Hemoglobin Gower 1, hemoglobin Gower 2, hemoglobin Portland. This is, what do you call this? বলো এইটা পাশেরটা এপসাইলন কে বলতে পারবে one who got the highest rank in NEET, probably he or she can do. Zeta, Z-E-T-A, zeta. Zeta 2, eta 2, alpha 2, eta 2, zeta 2, gamma 2. Hemoglobin Gower 1, Gower 2 and Portland. These are all embryonic hemoglobin. Clear? Now they are produced from these two chromosomes. See the chromosome 11 contains what? For adult hemoglobin, beta gene, delta gene for adult hemoglobin. Beta is altered beta, gamma, right? And epsilon. What is else? 16th chromosome contains the gene for zeta, embryonic state hemoglobin, and then alpha 1 and alpha 2. That means alpha gene for alpha subunit has got 2 copies in chromosome 16. Gene for beta subunit 1 copy in chromosome 11. Never forget, very, very important, these lines. Alpha 2 copies in chromosome 16, beta 1 copy in chromosome 11. The same chromosome 11 contains delta and epsilon. And zeta is a part of alpha. Zeta means alpha. So first one, the first type of subunit, alpha to beta 2, alpha to gamma 2, zeta to gamma 2. The first subunit will be synthesized from chromosome 16. Second type of subunit will be synthesized from chromosome 11. Never forget, very, very important. You remember this particular 2-3 slides, and you see the hematology will be easier like anything. Fine. With this background knowledge, now I am moving to the next slide. Before going to the next slide, you must be thorough with this knowledge. You must remember this. Keep this in your mind, head, before going to the next slide. Okay? থ্যালাসেমিয়া আসবো, এখন আসেনি, আগে হিমোগ্লোবিন তৈরি হোক। Now this diagram has multiple segments. This is types of cell above, top, megaloblast, macrocyte, normocyte. This broken line designates a time of birth. That means this is before birth, this is prenatal, this is postnatal. Clear? This is organs responsible for production of blood cells before birth. After birth from bone marrow, before birth from spleen, liver and yolk sac. Correct? So initially your yolk sac, then comes liver, then comes spleen, then spleen extends for a few weeks after birth, and then it is taken up by bone marrow. So now all the blood cells are being produced by bone marrow. Correct? Now tell me, shut up. Let me see your knowledge. Him and me. Can you tell which portion of our body is producing blood cells in my body and his body? So I live on production from flat bones, scapula, right? And he lives on production of a flat bone plus sternum plus, do we have sternum? Do we have sternum? Sternum epiphysis we have. It is now solid, but yours is still soft. I am producing, he is producing, but he is producing from the long bones too. I am producing from only flat bones. Correct? There are differences. Good. Now this is the blue line shows the initiation of production of alpha chain. It starts from percentage. This is a percentage. 6th week at prenatal stage, it starts picking up the pace. Then alpha continuous. Why? Because be it embryonic, be it fetal, be it adult, the first part is same, alpha. Only the second part is keeps on changing. So alpha will start from 6th week and maintain the same rate. This one, beta, will start from 6th week, but it will slow. It will start pick up after 32 weeks and then take a peak around 18 weeks after birth. Before 18 weeks, who is serving? Gamma. Before 18 weeks, gamma will serve the purpose, and then beta will take up. Soon after birth, delta form will start synthesizing and will maintain a very low level, around 15 to 20%. HbA2. These are Bohr hemoglobin. See, initially it was high, embryonic state. As soon as they enter the fetal state, it is decreased, eta and zeta. What takes up from here? Gamma. Gamma decreases sharply soon after taking birth. Now this gamma subunit is responsible for synthesis of fetal hemoglobin, and gamma subunit synthesizes from liver. So if a person shows high amount of fetal hemoglobin after birth, it shows which organ is affected. Liver. What kind of disease is this? Hepatic carcinoma. Fetal hemoglobin. Hepatic carcinoma. Right? So this graph is very, very important. You will find it in many books or in internet everywhere. Just remember it. Good. Now, these are the structures of hemoglobin and myoglobin. Hemoglobin is just like 4 times that of the myoglobin. if myoglobin contains one heme per globin group, globin chain, then hemoglobin contains 4 such heme group per globin chain. 1, 2, 3, 4. 4 globin chain, 4 heme group. Something is in between. What is this? This is a molecule called 2,3-BPG. This is a molecule called 2,3-BPG, 2,3-bisphosphoglycerate. Now the next question is, now you know the structure of hemoglobin, you know the structure of myoglobin. Now next question is, why myoglobin is used for storage and why hemoglobin, having the same type of structure almost, is used for transport. What are the differences they have in the function and why they have the differences like that? Do they have any structural dissimilarity which distributes their function in different way? Yes. What are those? We are going to explore that. So this question can be asked, describe the structure function relationship of myoglobin, describe the structure function relationship of hemoglobin, compare the structure function relationship of hemoglobin and myoglobin, explain why myoglobin is a good storage protein, whereas hemoglobin is a good transport protein, etc., etc. Describe the oxygen using curve of hemoglobin, show the different factors affecting the oxygen using curve of hemoglobin. Correct? All these questions have only one answer. This. Why? They are structurally different. Now, oxygenation causes considerable structural conformational changes. You know? If I don't have money and if I have a lot of money, you'll come to know by seeing me. You know? The moment a lot of money will come in my pocket, my attitude will change. Definitely, my shoulder will shake more frequently, and if I don't have money, then the shoulder will be down. You know? You can make out. Similarly, when the oxygen enters into the structure changes. How much it changes, and how it changes. Now, this is a very old diagram. This diagram shows two axes. Axis between two similar subunits of hemoglobin. Write down. Axis between two similar subunits of hemoglobin and axis between two dissimilar subunits of hemoglobin. That means axis between two alpha subunits and axis between one alpha and one beta subunit. There are two axes. These two axes will change. Which one will break? It will change by 15 degree. Okay, let me give you the information first. It will change by 15 degree altogether, totally, on addition of 4 molecules of oxygen. That means O2, 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 O2. 1 molecule of oxygen means O2. 4 molecules means O2, 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 O2. 4 molecules of oxygen, when added, it shifts its axis by totally 15 degrees. Addition of first oxygen shifts by 7 degree. Addition of second oxygen shifts is half of that, means 3.5 degrees. Addition of third oxygen shifts is by half of 3.5. Right? So which one is harder? Addition of first oxygen or addition of fourth oxygen? Which one is harder? Addition of first oxygen or addition of fourth oxygen? Which one is harder? Ulto bol dijo. Back. Bring this chair. Okay. Chair de. Chol. tum to matak. Diya. দিয়ে একশো তোর তুলে দে হ্যাঁ রাখতে হবে রাখ Tol. I am the fourth oxygen. How much force did I apply? So the fourth oxygen will be easiest to, correct? The first one has to shift it by 7 degrees. Break the bond and push the door so that I can enter. Suppose this door is closed. If I can push and enter the door, any Tom, Dick and Harry can enter. Why? Because I am the strongest, the first oxygen. Here I was the last. Right? I had to apply almost null force. I didn't apply any force at all. Similarly, these kind of system is called cooperativity. It's called cooperativity or cooperativity. That means addition of one molecule of oxygen will facilitate the addition of successive molecules of oxygen. একটা অক্সিজেন মলিকুল তার পরের অক্সিজেন মলিকুলকে ঢোকাতে সাহায্য করে। এটা বোঝানোর জন্য আরেকটা ছোট্ট এক্সপেরিমেন্ট বইতে দেওয়া থাকে, দেখবে এই পোস্টেজ স্ট্যাম্প চারখানা পোস্টেজ স্ট্যাম্প আছে। If you want to tear one out of 4, then what will happen? You have to tear first one till half, second one till half very carefully. If you have to tear now the second one from the 3, then from any type, any side you can tear one. And if you have to tear the last, then blindly you can tear, because there is only one way you can tear. You need not to see which side you are going to tear. Right? This is called cooperativity or cooperative binding. Now, which axis will be broken? This answer remain unanswered. The question that we will see from here. These are called salt bridges present. Draw the diagram. You might not find in book. These are called salt bridges. They are called salt bridges. That is the electrostatic interaction between the subunits, between the amino residues present in the different subunits. So there are two ways. See, this is alpha 1, this is alpha 2. They are arranged in opposite direction. Correct? Between two similar subunit, means two alpha subunit, how many salt bridges are there? 2. Salt bridges are formed between a basic amino acid and an acidic amino acid. See, lysine, aspartate, lysine, aspartate. See, lysine, aspartate, lysine, aspartate, arginine, aspartate, lysine, histidine. Right? Now there are two salt bridges between two similar subunits, alpha subunits, and there are one salt bridge between dissimilar. Dissimilar means one alpha and one beta subunits. So now you tell me, if you want to rotate this structure, which has greater probability to be broken, the salt bridges between similar subunit or the salt bridges between dissimilar subunit? Dissimilar subunit. Now can I go back to the previous diagram? It shifts by 15 degrees by breaking the axis of dissimilar subunits. See how you remember? Otherwise you have to mug up. If you know the reason, it's very easy. So if you know the diagram, this diagram, then you can describe the previous diagram. Okay? See, these chapters, if you understand how to remember, you can read anytime and you can remember. Because to explain these, the many books have used a lot of pages, which you will get tired or bored reading. Right? So, Presence of salt bridges signifies or dictates which axis to be broken during oxygenation of hemoglobin. These lines, what I am saying, is very, very important. Presence of salt bridges dictates which axis to be broken during oxygenation of hemoglobin. So it is the axis between dissimilar subunits which is broken down when oxygen is added and it shifts by 15 degree. What else? See this diagram. The top part, the solid line, refers to the heme plane. This is heme plane. Correct? What is heme? What is this? Pyrrole. We join 4 pyrrole ring, becomes porphyrin ring. Now this nitrogen has got 3 bond and this one got 2. Right? This is correct. Now this is a porphyrin ring which is present in heme. There are other compounds which contain different types of porphyrin ring. This particular porphyrin ring falls under (9A) series. Okay. Now, if an iron comes here, how many valency iron has? Huh? Highest. 6. K4FeCN6. Correct? Does it have any vacant d orbital? Yes. Four. This is behind the board. Behind the board. Proximal histidine, F8. 8th residue of F helix histidine. Suppose this is heme plane, this is iron, and here is a E7 histidine. Iron remains always below the plane or above the plane of heme? How many of you think iron is below the plane of heme? And how many of you think iron is above the plane of heme? How many of you think it is below the plane of heme? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, and above the plane? No one. Now if I add one more term, away from plane, how do you know which hemoglobin is standing upright and which hemoglobin is upside down? Are they human beings? Do they have any direction of standing? The molecules, right? Right? It can be in any direction. This chalk. Which direction it is? Below or above? How do you know? It is away from plane. Neither below nor above. Iron remains slightly away from heme plane. This is the concept you must grow when you are dealing with protein or three-dimensional structure. So iron is slightly away from the plane. But problem is the sixth position is taken up by oxygen or carbon monoxide. If it takes up carbon monoxide, it will be carboxy hemoglobin. It will be carboxy hemoglobin or carbamino hemoglobin. Huh? Carboxy hemoglobin. And if it takes up oxygen, that is oxy hemoglobin. Right? Now, the carboxy hemoglobin is like this molecule. Do you agree? So the bond angle is, an oxygen molecule is like this hemoglobin, this molecule. Bond angle is, right? Now E7 is located just on the head of heme iron group. Now if it is oxygen, then it will be bent. No issues. There is a clearance. But if it is carboxy hemoglobin, then stand. Histidine will hit. Which one? E7. So the presence of E7 will destabilize the structure of carboxy hemoglobin. That means initially E7 histidine will resist the entry of carboxy hemoglobin because you have to stand upright 180 degree straight. But if it fails to do so, why? Suppose carbon monoxide is concentration is very high, then the change it will take will be permanent. It cannot be reverted back. Whereas oxygen can easily stay. Low height, like this it will work. So oxygenation will be very easy. Right? The same thing is applied in this case. That is the role of 2-histidine. F8 is to hold the iron in place and E7 is to allow entry of oxygen. Clear? The moment iron attaches with oxygen, the iron moves towards the plane. How? Suppose this is a heme plane, correct? I am iron. I was here. If I move here, will it be nearer to the plane? Yes. the straight line distance will be less. It will not be counted from here. Perpendicular distance. Correct? Now, suppose I am here. Now I move here. Distance is same? Same. I moved, but distance is same. How it is possible? See? Correct? But when oxygen is attached, then iron is moved nearer to the heme plane. How much? By 1 angstrom. So difference will be 1 angstrom before and after oxygenation. When? In myoglobin. Whereas in hemoglobin, the same distance will be 0.2 angstrom. Difference. That means hemoglobin has got some extra factors. What are these? The cooperative function of the other subunits. Cooperative function of other subunits will help the iron to move nearer to the heme plane. If it moves nearer to heme plane, what will happen? The oxygen will just fit. Right? There will be no extra space. Oxygen will be just fit. And that will put pressure on oxygen. Why? I need to put pressure in oxygen. Why? Because oxygen, I need to deliver oxygen in the tissue. If oxygen is relaxed, then it will never come out. When oxygen is put under pressure, then only it will come out in the tissue level. Yeah? But these are all things which has been explained in these diagrams. This diagram, and this diagram. Now we come to this. Lastly, this graph. This is called oxygen dissociation curve of myoglobin and that of the hemoglobin. The curve is drawn from this side to this side, above to bottom, this side to this side. Myoglobin curve is hyperbola. Hemoglobin curve is sigmoidal shape. Myoglobin releases this graph. You need to draw in the examination. Difficult? No. I'll show you how to draw. What to read you will get it anywhere. I'll show you how to draw. Make grids like this, squares, by pencil. Okay? Then number them like this: 20, 40, 60, 80, 100, 120 up to 140. And here up to 100. Percentage, not more than 100. And this is mmHg, millimeter of mercury pressure, PO2. And this is percentage of saturation. Out of 100 hemoglobin, how many hemoglobin molecules are completely saturated? That is the percentage saturation of a particular hemoglobin. Here, see the graph of hemoglobin first. It is 20 at 20. 20% at 20 mmHg, the first point. Then 40 at 30. Forget this. 40 at 60. 20, 20, then 40, 60. Then this point, almost 80%. When? At 90. Almost 80% at 90. So draw, first you put these 3 dots. Then make a curved line. Hemoglobin graph is ready. Myoglobin graph is very easy. Finish the highest point, 80%. Here 80, Finish the highest point at 80%. Finish the highest point at 80%. 50%. 50%. This is 5. At 5 mmHg pressure difference, it will release 50% of its oxygen. Who? Myoglobin. Whereas hemoglobin will take 50% to release. See? Near about 38 mmHg pressure difference. Okay? So hemoglobin can transport across a wider range of PO2 difference in the tissue. Hemoglobin can transport oxygen at wider range of PO2 difference in the tissue. Whereas myoglobin, being located in a localized tissue, it will release all oxygen in one go. Yeah? The same thing is cooperative binding, which I have explained. The 2,3-BPG is a part of this particular function, responsible for particular function. 2,3-BPG exists between two beta subunits of the mature hemoglobin, HbA1, and it decreases the affinity of hemoglobin towards oxygen, so that at tissue level, hemoglobin can release oxygen, unload oxygen. See the location of 2,3-BPG. Right? Look at that. ऐसा तेल की लाभ नहीं, ठीक है? 2,3-BPG is located between two beta subunits of the what is Bohr effect? Presence of H plus ion will decrease the affinity of hemoglobin towards oxygen. Where do you find H plus ion? At lungs or at tissue? Tissue level. Tissue produces metabolites, H plus ion. So at tissue level, H plus ion, at tissue level, 2,3-BPG. Right? These all will help to unload oxygen from hemoglobin. At lungs, just opposite thing will happen. No Bohr effect, no 2,3-BPG effect reduced. So oxygen will be taken up. Can anyone tell me what is this diagram about? Let's take a photograph. This is called chloride shift. This is called chloride shift. See, at tissue level, CO2 enters, O2 comes out. Right? At lungs, just opposite. Just change the arrows, direction. Then it is called reverse chloride shift. So at tissue level, which helps in release of oxygen? Chloride shift. At lungs, which helps in taking up oxygen? Reverse chloride shift. And that is the thing which produces H plus ion, the Bohr's effect. Who is responsible for Bohr's effect? Chloride shift. Where do you find Bohr's effect? At tissue level. What does it do? It reduces affinity of hemoglobin towards oxygen so that it can unload the oxygen at tissue level. What is reverse chloride shift? How does it help in taking up oxygen? It reduces H plus ion concentration inside the RBC and hence negative Bohr's effect. This is the actual graph of oxygen dissociation of hemoglobin. There are factors which will shift the graph left side or right side. the graphs which will shift, the factors which will shift the graph right side is actually helpful for unloading oxygen, good for our health. The factors which will move it left hand side actually not good. What are those? High pH, decreased 2,3 dpg, decreased temperature. All these will shift the graph towards left. That means the tip of the toe will not receive oxygen anymore. Before the blood reaches the tip of the toe, the most distant part of our body, it will lose all its oxygen. Correct? So what will happen? Hypoxia, tissue necrosis. And in this case, lowering the pH means acidic. H plus ion is more. Bohr's effect. Increased 2,3 dpg. How? More RBC, more 2,3 dpg. In RBC, 70% of glucose molecule follow Rappaport-Lewering cycle, producing 2,3 dpg. Means out of 10 glucose molecules, 7 glucose molecule will follow production through 2,3 dpg. Not simple glycolysis. So these 2,3 dpg is produced more if RBC is more. When you have RBC more, when you are at high altitude or you are living in a community who goes deep diving. Correct? So your RBC number is more, called polycythemia, your 2,3 dpg is more. While running, your muscles will get more oxygen. So before polycythemia, you will be like me. After polycythemia, you will be like Sunil Chetri. Increased temperature. In warmer days, we feel more energetic than colder days.